All right, so we just ended a previous video on writing a decimal as a fraction when the decimal is a non-terminating repeating decimal. So we had talked about how to change non-terminating repeating decimals to a fraction. And we had done an example of 0.87 bar, okay? So we finished that one with these 4 steps, and now we're going to do a second example, 0.327 bar. So this one with 2 repeating decimals. So let's go ahead and start that example. And I do recommend you do the other example first as an easier example. Before this one. So we've got a decimal, and it's sort of repeating non-terminating decimal, just like it says right here. It doesn't end and it repeats. And so that means for sure you can change it into a fraction because it is rational. And by definition, rational numbers can be written as a fraction of integers. So how do we do that? That's the question. So remember step 1 and see if you can do that. Okay. In fact, you can pause the video and do as much as you can before you start it and see if you got to where you needed to go. All right, so let x equal the number. So x equals the number we're trying to convert. So that's going to be 0.327 bar. Step 2, we're going to multiply by a power of 10. So either 10 or 100 or 1,000, whatever number that has the number of zeros. The number of zeros should match the number of repeating decimal numbers. Okay. So basically, I have to choose 10, 100, or 1,000 based on how many repeating decimals there are. How many repeating decimals are here? 1, 2. The 3 does not count as repeating because it's not repeating. So only the decimals that repeat. So there's only 2 of them. So there's only 2 repeating decimals for step 2. So that means I need a number with 2 zeros in it. So that's going to be 100. So it has 2 zeros. So I'm going to multiply this by 100 and this by 100. So I'm multiplying the whole equation by 100 on both sides. So x times 100 is 100x. And this times 100 remember that when you multiply by 100, you move the decimal to however many places over as there are zeros. So 100 times that is going to be 32.7, and then the 27 repeats after that, so it'll just keep going. So 727 ... So 100x equals 32.72727, or 72, 72, 72. Step 3, subtract the original equation of x equals, from the new equation that we just made up with 100x equals. Subtract the original x equals equation from the new 100x equals equation. So, see if you can set that up. And let's see if I can just show this. So I'm going to take the new equation of 100x and then I'm going to take the original equation of x equals, and I'm going to subtract it below on both sides. So I'm going to subtract the x equals, and I'm going to subtract the 0.327. When I do that, notice that on the left side, 100x minus 1x is 99x. And then when I subtract here, 7 minus 7, all the repeating decimals after this, remember they keep repeating, but they're all going to repeat. So they're going to keep subtracting each other. 2 minus 2 is 0. 7 minus 3 is 4. 2 minus 0 is 2. So we've got a 32 over there. That was the hardest part, probably. So I'm going to do it one more time. Step 3, subtract the original equation from the new equation. So see if you can set that up. So the new one is 100x equals 32.727, and it just keeps going on and on. And then subtract the new equation, which is this. So I'm going to, or the original equation, excuse me. So I subtract the x, and I also subtract the 0.327. And I subtract that. On the left side, 100x minus 1x is 99x. And on this side, I subtract. 7 minus 3 is 4, 32. Step 4 is to solve for x. So that means when I'm solving for x, it's 99x equals 32.4. I have to divide both sides by 99. So my answer for x is 32.4 over 99. The only thing is I'm not allowed to have a decimal in there, so I have to multiply by 10 over 10. So it's 324 over 990. You can reduce that, but essentially remember that I have that x equals 0.327 bar. So that means that x as a decimal is this, but x as a fraction, which is exactly the same number, because they're both x, is going to be 324 over 990. So I have already converted it to a fraction, even if I didn't reduce it. Okay. So then the next thing is, let's see another type of problem you might see with rational numbers. All right, so it says classify each real number as either rational or irrational. So the first number there should be √2. And this one should be √4 over 9. Classify each as rational or irrational. Remember that anytime you have a square root that doesn't simplify, it is irrational. It's going to be a never-ending decimal, and it's not going to repeat. I know this looks a little bit like it's going to repeat because I only know the first 3 decimals, but let's see if I can fix that. Square root of 2 is 1.414213. So it's not repeating anymore. 21356. So and then it just keeps going and going, and it's not going to be repeating decimals. So that means that example 4a is a non-repeating, non-terminating decimal, so it's irrational. Square root of 4 over 9 is not irrational, guys. It's not. Why would it not be irrational? Take a minute to figure that out. You get square root of, this is because square root of 4 over square root of 9. I can do square root of 4 is 2, square root of 9 is 3. That actually is a fraction of integers. That makes it rational by definition. 4c, 0, 3 repeats, repeating over and over again. So that is actually going to be 2.03 bar. That makes it a rational number. 4d, this is not the same digits repeating, so it's irrational. I know that you've got 0, 3, 0, 0, 3. So the 3 is sort of repeating, but it's not repeating after the, it's not the same 2 digits repeating. It's not 0, 3. It's 0, 0, 3, and then it's 0, 0, 0, 3. So the pattern is not the exact same numbers repeating with the exact same number of each numbers. So that's going to be an irrational number. Not the same exact digits repeating over and over again. All right, number 5. Find a rational number R and an irrational number S between 1.51287 and 1.51288. There's a lot of answers, okay? So it's just got to be between 1.51287 and then 1.51288. So I can just take 1.51287 and add any number of numbers afterwards. So if I have that, it's bigger than the number before, which is 70, but it's smaller than 80. So my rational answer can be 1.51287, 1, and any number after the 7 as long as it's not just zeros. So that's one example. Another one would be 1.512872. 1.512873, 1.512874, so on and so forth. I could also choose 1.512870. Okay, so there's a lot of possibilities. I could even choose 1.512871 repeating, because repeating decimals are rational. An irrational number is a non-terminating, so it would have to be 1.512871213141. So anything that's not a repeating decimal. So this is a pattern decimal, but not a repeating one. So it has to be non-terminating, and it can't have the same numbers repeat over and over again. All right. Last question to kind of understand what irrational numbers are. So place these numbers on number line is the question. And let me give you those numbers. Pi, negative pi, root 2, root 9, and negative root 8. Those are the numbers we're going to put on a number line. So first you're going to make a number line. And I'm going to make my number line go up to say, -7. Hope that's big enough. All right, so pi is an irrational number. It never ends, but I can't estimate it. I can't estimate it so that I can put it on this table. So pi is roughly 3.14. So that's going to be between 3 and 4, and it's going to be awfully close to 3. So this is going to be pi. Negative pi is roughly negative 3.14. So that's enough to put on this table between -3 and -4. So that's going to be -4. Root 2 is roughly 1.4. Again, that's good enough for putting it on a table. It's also probably good enough for, tiling your floors, for example. Root 2, it's not exactly root 2, but it's close enough for putting it on, for many practical purposes. Root 9 is actually exactly 3. So that one I can put right exactly there. And then root 8, again, you can't find the exact answer to root 8, but you can put it into a calculator, which is what I'm doing, and get an estimate to get it onto a table that's good enough for our purposes. So that's going to be -2.8. That's going to be negative square root of 8. So just to say that even though numbers are rational or irrational, they can all be estimated to a decimal point. That's close enough for a lot of practical purposes. And that's it for some possible questions you could be asked about rational versus irrational numbers.